And I must start my today's session with the discussion of proof techniques. And this is the last topic of the section mathematical logic, which is unit 3 of our syllabus. Now, the things which will be discussed in this particular section is nothing new to you. You have done a great deal of this kind of proofs in your earlier days, in schools, in colleges also, because one of the topics, vector space, was there in the first semester course, which actually needed lots of proofs, and you have done so in your previous semester. Now, what you didn't notice while proving these things, that you didn't notice its technicalities because you didn't know the technicalities. What teachers asked you to write, or what he wrote in the board, you just followed him, but you didn't realize that why a particular teacher was doing that kind of using that kind of technique to prove something. In this particular topic, unit 3, proof techniques, you are going to learn what are the different proof techniques and how to implement them from problem to problem. And also I'm going to talk about what is the best proof technique, and or you can say the most useful proof technique used often in mathematics. It is wrong to say that it is often used in mathematics, because mathematics helps to build your logic, and that logic you apply to write the algorithm for computer program, be it C, be it Java, be it Python, whatever. You apply some algorithm. So the logic which is there, even in Microsoft Excel, when we apply the if-then statement, probably you have seen that in Microsoft also, if-then statement can be written. If this cell has this value, then that cell will have that value. Now, obviously, you can understand that there is hidden one sort of if-then logic gate behind the screen, which is not visible to us who are using the software, but we are using the logic. So mathematics helps you to build the logic, and you apply that logic in writing algorithms for the computer program. And building and writing that computer program needs a kind of mathematical logic, and that mathematical logic or proofs whatever you are doing needs a kind of understanding. So in proof techniques, the most fundamental part which actually we carry out, that always you remember while you study the proof techniques, that when we are faced with a problem, a mathematical problem, we try to make sure that the logic which we are building is complete, in the sense that it shouldn't contain any error, and at the same time we must convince others that the proof is legible. That means when others will read your proof, they must understand that what you are trying to say. Or suppose today you have done a proof by a technique, by a mathematical proof technique, and after that you are going to forget the rules which you have applied to prove the thing. So after 1 year, if you revisit your copy and you see your proof again, then again you must understand that what is happening, what was happening over there. So whenever someone is seeing your proofs, he must understand that everything has been taken care of. Every single line has been taken care of and is a valid mathematical argument. Now, there are some proofs which are very difficult to do. Say, for example, most of you know that there was a buzz around this particular proof. Last theorem of pharma. I am not going to discuss that because I haven't read it, and I'm sure that I'll also not understand because it contains rigorous mathematical treatment that I am not well aware of. Such a proof of this kind of significant theorems is actually, this proof is a 200-page long. It contains a rigorous mathematics. So sometimes most of us are not able to follow what is written in this kind of proofs, but a mathematician who is from the field of number theory or who is expert in this, who has expertise in this, he will understand. So such kind of theorems or proofs will not be such kind of proofs of theorems will not be discussed in today's class. In today's class, I'm going to show you the proof of some mathematical argument which are very fundamental and which are very easy and which you have already known. But you are going to learn here in this class how to deal with them. So to start with, I must say there are several techniques to deal with a proof. One of the technique that I'm going to discuss first is called direct proof. What is direct proof? In direct proof, we consider two mathematical statements, P and Q. Okay, and we make this statement P as my hypothesis, and suppose this statement Q is my conclusion. And my job is to show that this conclusion is following from that hypothesis. This is my job. Now you know that when you build the argument to reach from the statement P to statement Q, in between P and Q, you are going to write several other arguments. Okay, those arguments which have already been proved earlier or which are a valid mathematical statement. And you will make sure that in between these arguments, you shouldn't write something which is absurd. Now, the question is that when a particular statement is given like this, the question which comes to our mind that on the left-hand side of us, we have this statement capital P. On the right-hand side, we have the statement capital Q. In between, I'm going to write some lines, some mathematical statements, some mathematical arguments. Those are legible. The question is, what shall I write over here? How to find this out? What shall I write over here and how to find it out? And if I write a mathematical statement which directly follows from the statement capital P, a question naturally comes to our mind. Will it lead to my statement capital Q? Okay, because by the hypothesis capital P, if R1 can directly follow, there may be other statements which can also directly follow. So suppose from your mathematical statement, capital P, there is another statement which follows directly is R1 prime. Now, question is, shall I follow this path? Just a minute. Shall I follow this path or that path? Okay, so suppose this is my path 1 and this is my path 2, and I am not sure about it. Okay, so therefore, to build the logic in between capital P and capital Q, sometimes what authors or mathematicians do is that they try to convince themselves that Q follows capital P. So they start with Q and they kind of applies some backward methods to build that if Q is the conclusion, what conclusion from it was preceded by, and then what conclusion it was preceded by. So they try to find out, say for example, Rn, which follows from which the Q follows. They try to look at this in their mind, and then again they move some backward direction and they try to follow whether Rn minus 1 was preceding Rn, or whether Rn minus 2 was preceding Rn minus 1. In this way, and in your mind, if you all know there are two halves in the brain. So suppose your one half of the brain is actually thinking in this way, another part of the brain is progressing in this manner. So from P you are following, say R1, I'm talking about R1 here, and from R1 you are following, try to follow whether R2 is coming or not. In this manner, your brain is working from both the directions. From forward, this direction I'm calling as forward direction, and this direction I'm calling it backward direction. In between, somewhere at some moment, suppose at this point, I'm magnifying this particular region. Suppose at this point, your backward logic will coincide with your forward logic. And if this happens, if your backward logic coincides with your forward logic, coincides with forward logic, or vice versa, then you will conclude that yes, for that particular problem, you will be able to build a direct proof. You will be able to build a direct proof. If it doesn't happen, if your backward logic doesn't coincide with your forward logic, then you will not be able to build a direct proof, at least for the given mathematical problem or mathematical argument. Here I shall call the statement to be argument, because statement is a kind of, you already know that sentence is anything which we speak, that is called sentence, which is a collection of words, and with words which when combined together give you some sort of valid meaning. But statements are those sentences whose validity, such as truth or falsity, can be checked. Arguments are those statements, not only their validities are checked, but also one argument can be followed from the another argument. Okay, and if your argument is significant, then that argument, by significant I mean most scenario, in most situations, in various fields, your mathematical argument which follows from one, where one follows from the other, is actually applicable. We call such significant argument as theorem. Sometimes there are little theorems which come out of the mother theorem, Those little theorems are called lemmas, but lemmas are not actually significant, so we call them lemmas. Okay. Lemmas are sometimes also known as little theorem. Now, so what have we got in this particular page? So let us summarize what we have written. So my summary of the previous page is like this, that the construction of a direct proof, of the statement P implying the statement Q involves the construction of a string of statements such as R1, R2, ... Rn, such that P implies R1, R1 implies R2, R2 implies R3. In this manner, if we move on, Rn minus 1 implies Rn, Rn implies Q. Now, at this point, someone may ask, so if P implies R1 and R1 implies R2, and if R2 implies R3, and if R3 implies, and if in this manner, if it goes on, can I build Q from P? The answer is yes, and which comes from our previous knowledge on the mathematical logic and truth table. We have already known that the law of syllogism, if you can remember, states that if a mathematical statement R1 implies another mathematical statement R2, and consequently the mathematical statement R2 implies the mathematical statement R3, if they are true, then R1, the mathematical statement R1 actually implies the mathematical statement R3. This is known as law of syllogism, and that law of syllogism has been applied over here. And therefore we can say that if P implies R1 and R1 implies R2 and so on, and ultimately we reach at Q, then P implies Q. Now you can ask me one question, that whenever I have summarized the concept built in page 1 of my today's class, I didn't put arrows like this, that is from Q to P. I have written only one unidirectional arrow. Why is it that? I didn't write because that backward calculation is actually happening in your mind, and you are not implementing it for the time being. But this actually will be discussed, will be taken care of in some other scenario when we are actually going to test the by implication. So if someone asks me to test that, okay, show that P implies Q as well as Q implies P, so definitely we will try to write, okay, that P implies R1 and R1 implies R2 and Rn implies Q, and then again that will be my one part. My another part will talk about Q implies Rn and Rn implies Rn minus 1 and Rn minus 1 implies, and so on, R1 implies P. So in that case, the two directions will be taken care of in this by implication. But since we are only talking about unidirectional implication from P to Q, so I have written only one-sided arrow over there. So to show you the applicability of this particular result, this proof technique, let us try to prove a particular mathematical argument, which is actually very, I mean, primitive, and you have learned it in your school. Remember that your mathematical knowledge is not being tested in this particular class. I am not going to test your mathematical knowledge on abstract algebra, real analysis, vector space, probability statistics. I'm going to test your mathematical logic. And since most of us are well aware of what I'm going to write now, so I'm going to test my direct proof technique over there. So let's see. The square of an odd integer, the square of an odd integer is also an odd integer. The square of an odd integer is also an odd integer. So this particular result is a very well-known result, and I can say that in class 2 you have encountered this result in your school book. Okay, because the knowledge of even number and odd number actually starts from class 1. So that's why I have taken this. I'm going to test this direct proof technique from the perspective of mathematical logic. Okay, let's start. Let's start, and you try to follow. And if you have any doubt, you can raise your hand and you can ask me. Otherwise, you don't have to do anything. If we let small n stand for an integer, okay, then according to the theorem stated above, the hypothesis is, let us denote this hypothesis by capital P, that n is an odd integer. Just try to follow the suit. N is an odd integer. The conclusion, however, of the theorem is, denoted by Q, and we try to build an argument from P to check whether n squared is also an odd integer or not. So to check, to show whether P implies Q. So that is what I'm going to test right now. I said that I can build several arguments in between, and that is actually followed from my backward logic carried out in my mind. Now, I'm not going to show you the backward logic. The backward logic has already been done. So let's follow the forward logic only. We need the definition. We need the definition of odd integer, because we are talking about odd. And so we introduce the statement, R1, which states that n is twice k minus 1 for some integer k. Now you can see that when I'm saying that I wrote in the statement P that n is an odd integer, and we know this is the definition of odd integer, so we can say directly that P implies R1. Okay, so we want to deduce the statement, n square is equal to twice m minus 1 for some integer m. Since this would imply q. Okay, so my argument is, my logic is, I'm going to calculate n square. Now, if I can show that when we calculate n square, it is also in the form twice m minus 1, then I can say directly that, yeah, n squared is also a kind of odd integer. So let's follow. We have already got our, we had our capital P, we already got our R1. So let's see what comes next. So our R2, another statement I'm writing, that I'm writing n square. And since n is twice k minus 1, so I'm writing it as twice k minus 1 whole square. Now, we can write it as 4k square minus 4k plus 1. This argument has been built and it is a valid argument. So you have to check it again and again. Next, what we can write, we can do a kind of thing which goes like this. We can write it as 4k square minus 4k plus 2 minus 1. So we can write 1 as 2 minus 1. Okay, just look at this. Okay, then in R4, I'm going to write that n square as, take 2 common from this. So we get 2k square here in from this particular term. Here I am writing minus 2k. Here I am writing 1. And this minus 1 is separated. Okay, all together. Now you see, now obviously R3 is being followed from R2, R4 is being followed from R3, and therefore one preliminary knowledge will be required. Okay, preliminary knowledge will be required in this particular case, which comes from the property of integers, that when k is an integer, k squared is an integer, twice k squared is an integer, 2k is an integer, 1 is an integer. If we subtract one integer from another, that is also an integer. If we add 2 integers, that is also an integer. Now you see, all these mathematical arguments written over here is basic arguments which comes from the property of integer sets. I am not going to introduce these arguments over here because otherwise my proof will be unnecessarily long. When we build the definition of integers, when we built the properties of integers, we actually asked everyone to remember this and to apply them as when required. So every time you are not going to implement it in every proof, because otherwise it will be unnecessarily long. Now, if someone says that, okay, show that if k is integer, then this is also integer, then you can say, okay, then if it is capital P, then this will be R1 prime, then this will be R2 prime, then this will be R3 prime, R4 prime, R5 prime, and R6 prime. And P follows R1 prime is following, P is followed by R1 prime, R2 prime is followed by R1 prime is followed by R2 prime, and so on. But this is my what I'm going to prove over here. So I have considered this particular part to be true by knowing that it is true, and my objective is fulfilled. Now I can say, I can write this as twice m minus 1, where I can at least say from the property of integers, from the property of integers, m is also an integer. M is also an integer. And not only this, you see that this n square term is actually of the form twice m minus 1. When n is an odd integer, so its term is of the form twice k minus 1. So n square is all of the form twice m minus 1. So actually, we are getting something that we wanted to get. So now we can say from this that, okay, your P implies your statement R1, R1 implies your statement R2, R2 implies your statement R3, R3 implies your statement R4. And this R4, you see, at least we can add over here one more statement, that Q, which was my statement that n square is an odd integer. So R4 implies Q. So from syllogism, from law of syllogism, P implies Q, which means that when n is odd integer, then n square is also an odd integer. So let me write it. So this implies, where shall I write? Okay, let's make some space over here. So when n is odd integer, then n square is odd integer. And not only this, I'm going to the next page. You are going to see that this statement can also be written in the following way. For all n belonging to the set of integers, n is odd implies n square is odd. And we used to write, after completion of the proof in school, we used to write this particular word, isn't it? Proved. But somehow we have got to know about writing proved in our earlier classes. I also did so in my class because my teacher told me to do so. Or sometimes people write shown. Now, when you will see a mathematical journal or mathematical paper, you will see that when a particular mathematician completes the proof, they don't write proved or shown. They write something else. It is called QED. What does QED means? QED means quod erat demonstrandum. This is a Latin word which means which was to be demonstrated. Which was to be demonstrated. So whenever we finish a proof, we write QED because in mathematical community, this is universally acceptable. So whenever you write QED, that means you are actually telling people that you have completed your proof. Now let us analyze the proof which you have done once again. You started with P, which is an odd integer. R1 is actually, in R1, you have written a statement which actually comes from the definition. So it is quite obvious. And as you actually you are interested in finding n square, so it is also quite obvious that you will square that thing. Okay, because we are interested in the square of the integer. So it is obvious. Which was the thing which was not obvious is this portion. And this is the trick that you are doing over here. So every mathematical proof is associated with, may or may not be associated with a trick. So this is the trick which is actually been followed. And if you forget this trick, then probably you will not be able to follow R4 and as well as Q. So sometimes your teacher used to tell you that, yeah, we have done a mathematical proof and this mathematical proof needs a trick, and this is the trick. Why is the trick? Because how this particular thing have been obtained? How do you know that we want to write one from we want to express 1 as 2 minus 1? How do we know that? We know because we started with, in the back of our mind, we started with Q, we went to R4, and then we went to R4, R3, and then we went to R2, and we know from this our backward calculation that, yeah, something has to be done in this part. But this backward method is not also very obvious method. So this technique, although this result is very, I mean, well-known result. So technique is actually very interesting and you have to follow it properly. So I'm going to demonstrate 2 different proof techniques in my second session. I'm stopping the recording for now.